Hello and welcome to another video on orbital mechanics. I am going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, and I'm up to problem 1.13. And problem 1.13 is again following on from the previous videos, and what it wants us to do is derive expressions for the angular velocity and the angular acceleration for this aeroplane in the picture. So here we have an airplane flying overhead, and we're assuming a flat Earth, unfortunately. It's flying overhead at a constant velocity in this direction, and at a specific height. It starts from this position in the picture, but we can assume it's anywhere along this path, and it's at this angle to the ground. There is a radar station here, which is tracking the plane, and as the plane moves, I think we're to assume that the radar station is rotating with the plane, and this line here and this line here represents our moving frame that is created by the rotation of this radar station. So we have our inertial frame, X, Y, and Z, and we have our moving frame, X, Y, and Z, again into the page. So in order to get a value for theta here, we can use some fundamental trigonometry. So we know that the velocity, we have the velocity going in this direction, and that takes a specific amount of time. So that distance here is the velocity times the time. Distance equals speed times time. So this is going to be tan theta equals Vt divided by h. And if we take the derivative of both sides, the velocity is a constant, as we said. So the Vt here becomes V over h. And this one, the derivative of tan theta is sec squared theta. And we bring out the theta, which is time dependent. And the derivative of that becomes the angular velocity. And then if we rearrange that, angular velocity equals V over h sec squared theta. 1 over sec squared theta is cos squared theta, and so that's our final expression for angular velocity. And the vector for that is going to be just into the page, right? So that's how your angular velocity works. It's perpendicular to your actual rotation. And then if we take the derivative of that again, the derivative of angular velocity is angular acceleration, and the dt of this, we've just simplified it into cos theta. So that's the product rule, and so we end up with minus sine theta cos theta w, angular velocity, plus the negative sine theta, again it's the same. So we end up with two of those. So minus 2v over h, sine theta cos theta, and then that angular velocity is up here. So we bring that back in here, and then we multiply out our terms, and we get, that's our final expression there. And our angular acceleration as a vector is going to be along the same vector as angular velocity. So we get the unit vector for angular velocity and multiply it by our angular acceleration. So that's that. And the book also asks us to derive the relative velocity. So in this example, as the plane moves, this line here moves with it, and theta increases. So if you imagine this plane going to very far away, like say, 100,000 kilometers away, this line is going to become almost horizontal. And that means the velocity here is going to be the relative velocity is going to match the velocity of the plane, because, it's going away from me and it's also moving in a straight line, but those two things are the same. So as theta approaches 90 degrees, V equals relative V, And when it's at 0 degrees, the relative velocity is virtually 0. It approaches 0 as theta approaches 0. And so we can say that, and if we look at this, it's essentially going to project this vector onto the relative velocity here. And we know that's a relative velocity based on what we just said. We'll project that onto it, and we get relative velocity equals v sine theta. Okay, and then the relative acceleration is the derivative of that, which is angular velocity times velocity cos theta. Cos theta being the derivative of sine theta. And we know the acceleration absolute is 0 because we're told the velocity is constant. And then if we go down here, we have another way to derive the relative velocity using the equation from the book. We have velocity minus the moving frame velocity, which actually is 0, minus the angular velocity cross product with the r vector. So that's the rearrangement of the equations that you've seen before in problem 1.2, 1.12, and in the chapter. And then the relative acceleration vector, again, we can get it this way. So we can say that a bar, and this is 0 because that is 0 up here. So the acceleration vector, the absolute acceleration vector is 0. The acceleration of the moving frame is 0. And then we subtract the rest of our acceleration formula, because we rearranged it so that it becomes negative. And so that gives you that. And that is basically it. You can also take this, if you take the acceleration relative here, so a relative times I of the moving frame, that equals, this is I here of the moving frame. That's the I vector, that's the J vector, the K vector is going in. And it's the same for the velocity relative times I equals, sorry, don't put that there, equals velocity relative. So these are the vectors. These are your vectors. All right. So, yep, that's it all there. This wasn't asked for, but I did it anyway, just for completeness. If you have any questions, leave them in the comments. I will answer them. Thank you very much. Goodbye.